In this video, we'll go over the basics of a voltage-controlled oscillator. We'll see how we can use it as a building block for audio applications. They can be used in synthesizers or to stand alone as tone generators. This VCO might remind you of a 555 timer, but usually VCOs are a little more versatile in audio applications. This is the VCO I'm going to be working with. It is the XR2209. It has a frequency range that's both well beneath and above what we can hear, and has simultaneous triangle and square wave outputs. We'll focus on these two parameters in the duration of this video. We can see in this block diagram that it is controlled by a timing resistor and a timing capacitor. This simplifies our design and makes it really easy to work with. For single supply designs, we want to bias the circuit to have a DC offset. In addition to these few components, we have a few bypass capacitors which help the VCO's performance. This chip is nice to work with because it produces a square wave and a triangle wave output. Here's a look at the VCO on the breadboard. It uses an 8-pin DIP package, which stands for dual inline package. From this bird's eye view, we have pins 1 through 4 on the left and 8 through 5 on the right. Using the single supply design referenced on the datasheet, I laid it out on the breadboard. We'll take a look at each connection starting with pin 1, which is VCC or the supply voltage. Note that there's also a bypass capacitor here which connects to pin 1 and ground. This helps with the performance of the VCO. Next, pin 2 and 3 are for the timing capacitor. Then the last pin on the left side is the timing resistor, which connects from pin 4 to ground. Here is a side view of the left side. Now let's take a look at the pins 8 through 5 on the right side, starting with pin 5, which is for the bias resistors. These resistors are equal value, share a connection at pin 5, and have two different connections on the other end, which is for VCC and ground respectively. These connections set up the voltage divider, which is half of VCC. There is also a bypass capacitor for performance of the VCO. Pin 6 is connected to ground in the single supply design case. Pins 7 and 8 are for the output. 7 is the square wave output, and 8 is the triangle wave output. Note that there is a pull-up resistor for the square wave output, which connects from pin 7 to VCC. Here is a last look at the right side. Let's check out the output on the oscilloscope. Here is the triangle wave output. Its amplitude is about half of the supply voltage, which is 12 volts in this case. The amplitude of the peak-to-peak voltage is in the range of 6 to 7 volts. The frequency measured is about 4.36 kHz. This is due to the selection of the timing resistor and capacitor, and we'll take a look at this in a few moments. Here's both outputs at the same time. The square wave is channel 2 in yellow. Its amplitude is roughly equal to the supply voltage, and its frequency is just about the same as the triangle waves. The VCO's output frequency is easy to calculate in this case. The output frequency equals 1 over the timing resistor times the timing capacitor. For this circuit, the timing resistor was 22K and the timing capacitor was 0.01 microfarads. The result of this is about 4.55 kHz. It's important to note that this is the ideal case for the output frequency. Looking at the actual measured frequency out, we see that there is some error. I'll point out a couple of things that contribute to this error. One thing to note is the resistors you're using. I'm using 1% threshold resistors. What this means is that the actual value of your resistor is within 1% of what's specified. So 220 ohms can be the maximum and minimum errors in our case. We'll look at the minimum threshold first. We take 22,000 and subtract from it 220. We're left with 21,780 ohms. This is the new value of the timing resistor. We plug it into our frequency out calculation and we get it equaling 4,591 Hz. We'll do the same calculation for the maximum error. The new value for the time resistor is 22,220. The resulting output frequency is 4,500 Hz. This means that if this resistor is 1% off, it contributes 45 Hz of error to the total output frequency. Although this is probably not the dominating error in my circuit, it's just to demonstrate that little things can add up. Each component added into the circuit can add errors such as this, just like errors in the capacitor's value can. A quick look at this plot from the datasheet shows that the frequency accuracy is related to the value of the timing resistor. A takeaway from this analysis is that you should expect that your frequency out might deviate a little bit from your ideal calculations, but the frequency out equation for this circuit is pretty accurate and is a good place to start with. You can add a potentiometer into the mix and start varying your resistance on the fly. I added a series potentiometer with the timing resistor. This allows me to change the output frequency based off the changing value of the timing resistor. This is the first basic way to start generating new kind of interesting tones and update the output based off some changing input. Thanks for watching and stay tuned for more videos on this VCO and other content.